Let's do a couple examples of refraction here that look a little bit different. So usually we've been using the wave ray because it's simpler and it's a little bit more straightforward to show what's happening with refraction. But the examples that we have here are given to you using wave fronts. Now you should be able to do that as well. Mostly just because it's not very hard to draw in the wave ray really quickly when you're given the wave fronts. Okay, now we've been given a set of things to do with this diagram. We don't necessarily have to do them in this order. You can do them in whatever order makes the most sense to you. So the first thing that we're asked to do is label the dense and rare portions of this set of waves. Okay, and so one side on the left is either dense or rare, and the right side is either dense or rare. So we can make that decision a number of different ways. We know that everything is smaller on the dense side and everything is bigger on the rare side. And so the first thing I'm going to look at is the wavelength, because I think that's the easiest to see. So I can see that on this side the wavelength is this big, and on this side the wavelength is this big. This side, the left side, looks smaller to me, and so I'm going to say that that must be the dense side, because the wavelength is smaller on the dense side. And that means this is the rare side. Okay, that's not the first thing that you had to do in order to figure everything else out, but it's a good place to start. Label the wavelength on each side. I'm going to do that in black as well. So the wavelength is from here to here. That's the wavelength on this side. And then the wavelength on this side is from here to here. Then we're supposed to draw the wave ray. Now the wave ray is just the arrow that shows you what direction the waves are traveling in. So the wave ray is always perpendicular to the wave fronts. I'm going to start my wave ray over here, right over here, because that's going to be the easiest for the rest of this stuff. Okay, so I need to draw it perpendicular to the wave fronts, and I'm just going to do my best. It might not be perfect, but we'll give it a shot. So there you go. So there's the wave ray, the incoming wave ray, or the incident wave ray, and then the outgoing one, I have to draw it perpendicular to this side. Something like this. There you go. There's the refracted ray. So I've drawn the wave ray on both sides. Now I'm supposed to draw the normal line to the boundary. Now I'm going to draw my normal line where I've drawn these other two things, where I've drawn the wave rays to, because that's going to make my measurement of the angle of incidence and refraction easier. Okay, so my normal line is just perpendicular to the boundary. So it looks like this. This is my normal line. And so now we can draw in the angle of incidence and the angle of refraction. So the angle of incidence is between the incoming wave ray, or the incident wave ray, and the normal, and the angle of refraction is right there. So this is, I'm going to call it theta 2, but you can call it theta r if you want to, and I'm going to call this theta 1, but you can call it theta I if you want to. Incident and refracted, or 1 and 2. Totally fine. In which side do the waves move faster? Well, we could probably answer that from the very beginning. If we knew that this was the dense side and this was the rare side, well, things move faster in the rare side, right? Everything is bigger, everything increases in the rare side, and so the wavelength is bigger, the angle is bigger, the speed is bigger. Okay, and so the waves move faster in the rare side. How do the frequencies compare? That is the one thing that does not change, right? So v equals f lambda, speed equals frequency times wavelength. So the speed changes, the frequency does not, and the wavelength changes. So the frequency on both sides is the same. So I'm just going to say f1 is equal to f2. Now we're going to answer the same questions about a second set of waves, just to make it hopefully a little bit clearer. So we've got wave fronts moving, let's call it north. So the wave fronts are moving north, and we've got this angled boundary over here, and then obviously the wave fronts are changing direction quite drastically. Okay, so we've got refraction going on here. Again, I think that the easiest way to figure out which is the dense and which is the rare portions are looking at the wavelength. So the wavelength here, I may as well draw that in right away. This is the wavelength on this side, and this is the wavelength on the other side. So this side, its wavelength is smaller. I can tell that. It's basically one block on this grid, and the other one is more than that. The other one is pretty much one diagonal grid marker, and so that's bigger. And so that means that this one must be the dense side on the left and the rare side on the right. Because the rare side, everything is bigger. Everything increases on the rare side. Okay, so we have the wavelength, we have the dense and rare portions, and now we're supposed to draw in the wave ray. So I'm going to again pick a junction spot over here because that'll make it the easiest. The incoming wave ray is very simple at this point. It's like this. Okay, this tells us the direction of motion. So we know that the wave fronts are moving this way. So really this arrow that you're given over here, this is the wave ray. We've just got to put it somewhere where it makes sense. And then we need the refracted ray as well. And oh boy, it's like I have to turn my head really far to figure out how to draw this one. But it goes something like this. There you go. It's a really wiggly line, but that's the idea. So we've got the wave rays. Now we want to draw the normal line so that we can draw in where the angle is. So the normal line is perpendicular to this, perpendicular to the boundary. So something like that. Then we can draw in the angles. So the angle is between the normal and the wave ray. And so our angle of incidence is right there, theta 1, and our angle of refraction is right over here, theta 2. Notice that the angle of refraction is much bigger than the angle of incidence. Okay, and that makes sense. If that follows our rule, everything increases on the rare side, everything decreases on the dense side, and so the angle got bigger when we move to the rare medium. Then we're supposed to say which side is faster. So the rare side is always faster. Speed, wavelength, and angle all increase on the rare side. And how do the frequencies compare? That's always the same. The frequencies on both sides are going to be equal. So finally, F1 is equal to F2. But that's always the case. Our final refraction example looks a bit different again. The following wave ray reaches a boundary as shown. Now we're talking about the ray again, and not the wave fronts. Part of the wave is reflected, and part of it's refracted. Okay, we saw that with the simulation. Draw the reflected and refracted wave rays. The angle of incidence is 30 degrees. Okay, so this is actually important to be accurate. It says that the angle of incidence is 30 degrees, and it wouldn't say that if it didn't want us to actually calculate where the refracted wave ray was supposed to go. So we're going to actually have to do a calculation on this one. So first of all, we've got this incoming wave ray, or the incident wave ray. And I think that at this point, I want to draw in the normal line, because that's going to make everything easier. So the normal line is perpendicular to the boundary, something like that. And so now I can draw in the angle of incidence, which is right here, or theta 1. And then it tells me that this is 30 degrees. That's the angle of incidence. I then can draw in my reflected wave ray, because if we remember the law of reflection, it states that the angle of incidence is equal to the angle of reflection. The incoming wave ray bounces off the boundary at the same angle it came in at. So it looks something like this. It's not perfect, but that's close. So this right over here would be the angle of reflection. I'm going to call that theta r. Okay, angle of reflection, but still, it's just 30 degrees because our incoming angle was also 30 degrees. Then we're supposed to figure out what is the angle of refraction. So that's going to be in here somewhere, but we don't know exactly where. But we can figure it out. So we know that sine of theta 1 over sine of theta 2 is equal to v1 over v2. That was one of the parts of that relationship that we discovered in the previous video. So we know v1 is 2 meters per second, we know v2 is 3 meters per second, and we know the angle of incidence is 30 degrees. So we can solve for the angle of refraction because we've got 3 pieces out of 4. So let's rearrange it for theta 2 first of all, and then we can put all the numbers in. Again, you can put the numbers in first, and then simplify, and then rearrange if you want to, but I prefer to rearrange first. So this is on the bottom right now, so I need to multiply by the sine of theta 2 to get it out of the bottom, and then I need to divide by v1 over v2. Okay, dividing by v1 over v2 is the same as multiplying by the reciprocal, if you recall, and so it ends up looking like this. Sine of theta 1 times v2 over v1 is equal to the sine of theta 2. Okay, so when we solve this, we're going to get the sine of the angle that we're looking for, and then we'll need to do the inverse sine in order to actually solve for the angle of refraction. So let's put in all our numbers here. Sine of 30 degrees times 3 meters per second divided by 2 meters per second is equal to the sine of theta 2, the sine of the angle of refraction. So the sine of 30 degrees is 0.5. 0.5 times 3 is 1.5. 1.5 divided by 2 is 0.75. So 0.75 is the sine of theta 2. And so when we do the inverse sine, we get theta 2 is equal to 48.6 degrees. So that's our angle of refraction. So now we can draw in where that ray goes. So 48.6 degrees, that's near 45 degrees. And so I'm going to draw this split in half here, because that's close enough. And the angle of refraction is this one right over here. This is theta 2, and that's 48.6 degrees. Okay, so we knew how to draw some things because of the law of reflection. We knew where to draw the normal line, and so we could draw in the angles, and then we had to use one of the relationships. We had to use the angles and the velocities, or the angles and the speeds in this relationship. But in some of the practice that you're going to do, you may have to use the angles and the wavelengths, or the wavelengths and the speeds, because this is a 3-part relationship between the angles, the speeds, and the wavelengths.